Hello, this is Ben Zandi of TES International. I would like to welcome you to this webinar on how to use ThermoFlo to speed up your engineering calculations. We start with the introduction of the software, and then we'll discuss how it can be used as an engineering calculation tool. We'll demonstrate that using 5 examples on pumping and flow distribution, heat exchanger analysis and design, and then thermodynamic analysis for components and cycles. ThermoFlo is an advanced modeling and simulation tool for analysis and assessment of thermal management system capabilities. In a ThermoFlo model, a complex system is divided into parts and flow paths with direct interaction and coupling between air, liquid, and refrigerant loops. To construct a model, the user selects the parts, connects the parts to define flow paths, chooses a fluid for each loop, then sets the loads and boundary conditions, and runs the simulation. To define the fluid, the user can choose from the vast selection of NIST fluids library, or optionally define a user-defined fluid. ThermoFlo parts are completely customizable and are selected from the parts library. The user can easily create new parts or modify existing parts to save to the library. There are 3 types of parts to choose from. Simple parts are entirely defined using a single entity. Complex parts are defined using a group of simple parts, but displayed on the screen using a single icon. 3D parts are parts that their behavior is predicted using a coupled three-dimensional thermal and/or CFD model. 3D parts are only available when ThermoFlo is accessed from TE Suite Variable Fidelity Analysis package. Double-clicking on a part icon results in opening the Parts Properties menu. Here the user has access to all user variables and can set values as constants or functions and choose a unit for each. If a variable is left unchecked, its value will be calculated if there is enough information, or its effect will be neglected. Here on this form, the compressor pressure ratio will be calculated, but its kinetic energy and potential energy effects are neglected because there are no information for the height change and inlet-outlet areas. In ThermoFlo, the part's behavior can be controlled using complex mathematical expressions utilizing functions and tables, with the table defining ranges for the independent variable and a function to prescribe the behavior in each range. This example shows a possible behavior definition of an orifice using the ratio of length over the throat diameter as the independent variable, and prescribing 2 functions corresponding to the 2 ranges shown. Note that the MathLook window illustrates the algebraic expression in a convenient form as the user enters the function. Also, in a function, the user can choose any solver variable or point to another defined function or table. In this example, A12 represents the ratio of the throat diameter to the duct diameter obtained from a table called A12. In this webinar, we will focus on the basic or core functionality of the software to demonstrate how it can be used to solve classic engineering problems with ease. Using ThermoFlo in this capacity relieves the engineer from the tedious, time-consuming, and error-prone procedures that requires table or chart lookups for fluid properties and performance evaluation. I will present this using 5 examples involving pipe systems, heat exchangers, and thermodynamic analysis of components and cycles. In this first example, we are looking at a water flow in a pipe system that's pumped to upper levels of a high-rise building from a ground reservoir. In the first scenario, that I'm calling scenario A, we want to determine the pump power needed to deliver 4 kilograms per second of water to the 20th floor, assuming it's 100 meters high, through 1000 meters of 5 centimeter cast iron diameter pipe with a roughness of 0.26 millimeters. There are some minor losses that are identified and shown here. These losses must be included in the solution procedure as well. Start ThermoFlo, then click on Create Model. Give it a name, for example, pipe underscore complex. And then we click on Save. Now we choose thermodynamic cycle. And from the components, we choose pipe, drag and drop it on the canvas. Now we take an endpoint, place it at one end, and we take another endpoint and put it on the other end. Connect the components. Right-click on any connection point and set to fluid. Water is the default, so we keep it that. Now we double-click on one endpoint, define inlet, give mass flow rate of 4 kilograms per second, set pressure to 1 atmosphere, temperature to 20 degrees Celsius. Apply to define it. Double click on the other endpoint. The only thing we need to define here is pressure. We make it 1 atmosphere. So there's no change in pressure. Now we will double click on the pipe to give its properties. We set the diameter to 5 centimeters, length to 1000 meters. Now we check the pipe losses on and enter the minor losses, 9.5, and give a surface roughness of 0.26 millimeters. Click on Advance. We uncheck pump power because we want to calculate it. Give the pump efficiency to 80%, and we set the height change to 100 meters. Press Apply, and we're ready to run the problem. Click on Run and get the results. Now we open the out file to look at the detailed results. The endpoint calculated results are written. Notice that minus 999 means liquid, compressed liquid. Velocity, area, everything is calculated. And then we look at deduct results, and all the calculated results are there. Pump power is calculated to be 1159.2 watts. Now let's look at a variation on this type of problem. In other situations, you may know the pump power, but you may want to solve for the height change, mass flow rate, pipe diameter, friction, or other losses. As we know, some of these require iterative procedures that can be time-consuming. With ThermoFlo, we can do these calculations easily by making a simple change and rerunning the problem. To show this, let's consider scenario B. Here we want to determine the mass flow rate of water that can be maintained by a pipe system using an 11.6 kilowatt pump with the efficiency of 80% to deliver water flow to a height change of 100 meters through 1000 meters of 5 centimeter diameter pipe. First double click on the pipe, then we go into its properties, turn on the advanced properties. We'll check the pump power to enter 11.6 kilowatts. Press Apply to save the properties. Now we double click on the inlet and we uncheck the mass flow rates because we want to calculate it. Now you press Run to solve. Now we reload the results. If you look in the out file, We can see the results displayed as before. Mass flow rate is calculated for the pump work of 11.6 kilowatts to be roughly 4 kilograms per second. Now let's consider a multiple pipe scenario. In this piping system, all pipes are concrete with a roughness of 0.04 inches. Neglecting minor losses and assuming a flow rate of 1200 cubic feet per minute, we want to calculate the system pressure drop and the flow rate in each pipe. Click on Create Model, give it a name, and press Save. Now we go to the component template and choose a straight pipe and place it on the screen. Double click to enter geometric parameters. Here we have 1000 feet long and 12 inches diameter. Press Apply. Now we want to copy this part, so we keep the control down and drag the pipe into 4 other places to create the 4 additional pipes. Now we double click on each one to change its geometric parameters. This one has a length of 1500 and diameter of 8. This one is 800 feet long and we keep the diameter at 12 inches. Next one is 1200 feet long with 15-inch diameter pipe, and the last pipe 10 feet long and keep the diameter at 12 inches. Now we need to get an inlet and outlet. So we place the inlet right here and we need an outlet on the other end. Now to connect multiple pipes we need a connection node. So we drag a connection node, place one on this side and one on the opposite side. Now all we need to do is just connect the nodes to each other to complete the system. And the other end. Okay, now connect the inlet and the outlet. Okay, now we need to choose the fluid. So we right click on the node and we keep water as the default fluid. So let's set the inlet flow rate. So we turn it on and we enter 1200 and choose the unit as CFM. Press Apply. Okay, that sets up the problem. All we need to do is run it. And now we can look at the result. So we go first look at the pressure result or flow rate. Let's look at the flow rate first. Look at the mass flow rate in kilograms per second. Or volumetric flow rate. Default unit is CFM, so we can see how the flow is distributed in the piping system. And now I can change the result to pressure and see the pressure in pascals, pressure drop, or PSI. Now let's see how ThermoFlo can be used to solve classic heat exchanger analysis and design problems using the methods developed by Case and London. The solution procedures for these problems usually involves chart lookups for effectiveness and NTU for various types of heat exchangers. All these are programmed in ThermoFlo. As we mentioned earlier, the user can optionally define their own heat exchanger behavior based on their experimental data as well. In this example, we're going to look at air at 300 degrees Celsius at the rate of 1.5 kilograms per second that's used to heat up water at 35 degrees C and a flow rate of 1 kilograms per second. We have a cross-flow heat exchanger with both fluids unmixed, and we have a gas side heat transfer coefficient of 100 watts per meter squared C and the area of 40 meters squared. We want to determine the rate of heat transfer by this heat exchanger, and we want to know the effectiveness and the air and water outlet temperatures. Click on Create Model and give it a name. Now we go to the Components library and choose Cross-Flow Heat Exchanger. Place it on the screen. We need an inlet and outlet for the first flow path, and an inlet and an outlet for the second flow path. Now we connect the nodes to define the two flow paths. Right-click to set the fluid for the first flow path. Double-click on the icon and choose air from the list of the fluids. And we'll do the same for the second flow path. Now we choose a fluid. Water is the default, so that's fine. We keep it. Double click on the inlet to set its properties. Mass flow rate is 1.5 kilograms per second. We set the pressure to the atmospheric pressure. And temperature to 300 degrees Celsius. Apply. Now for the second flow path, the mass flow rate was 1 kilogram per second. Again, we choose the pressure as atmospheric. Temperature 35 degrees C. Now we double click on the heat exchanger to set its user properties. We leave NTU unchecked, will be calculated. UA is the product of heat transfer coefficient and area, so that would be 4,000. Epsilon would be calculated. Everything else left unchanged. If you wanted to add some losses, you click on it and you can enter the values. So we leave everything else unchanged and click on Run. The results are loaded, and if you right click as before on a component, you can see that the epsilon effectiveness is 83%, and all the other properties calculated. The outlet temperatures for the two flow paths are also calculated as well. Now we want to use ThermoFlo to solve problems involving thermodynamics. In the first problem, we look at thermodynamic analysis of a component. Here we have helium to be compressed from 100 kilopascals and 300 degrees Kelvin to 500 kilopascals and 600 degrees K. It was determined there was a heat loss associated with this process of 26.6 kilowatts. Neglecting kinetic energy and potential energy losses, we want to solve for the actual power input required for a mass flow rate of 80 kilograms per minute. We also want to solve for isentropic efficiency of the compressor, the reversible power input, the second law efficiency of the compressor, and the rate at which exergy is destroyed. First we start ThermoFlo, then we click on Create Model, give it a name like HE-Comp, and then click on Save. The file name exists, so we overwrite it. Now we go choose thermodynamic components. Now we pick compressor and place on the canvas. Now within an endpoint at one side to be the inlet and another endpoint for the outlet. Now we just connect the parts together, the outlet to the inlet of the next endpoint. Now right click on any connection point to select the fluid. Water is the default, double click on it, so we change from the list of NIST materials to helium. Now double click on the inlet, give it a name, inlet, set mass flow rate to 80 kilograms per minute. Now we set the pressure, click on the pressure, set 100, set the unit to kilopascal. Temperature set to 300 degrees Kelvin. Press apply. Now we set the outlet conditions. Double click on the outlet, give it a name. We set the pressure to 500 kilopascal. Now we set the temperature to 650 degrees K. And apply. Now to set the compressor properties, double click on the compressor. There is a heat loss of 26.6, so we have to use negative 26.6 kilowatts. And we uncheck the efficiency to calculate it. You can set the surroundings to 20 degrees for second law calculations. Press apply. Now we're ready to run. Click on run, and the results ready. And if you right click on the compressor, we can see the abbreviated results. Shows the power in and efficiency, isentropic efficiency. There is no kinetic energy and potential energy because we chose to ignore those things. Now let's say we wanted to include kinetic energy. So double click on the compressor and we go to the inlet and outlet conditions and we just enter the area. Let's say 0.5 meters squared. Now there is enough information to calculate the velocity, so kinetic energy will be included. You run again, and we have the results. Again, if now you look at the compressor results and you see there's 149.58 watts of loss in kinetic energy. Now to see the detailed results, we can open the out file by going to the folder and editing. The properties are shown at the top. You can see all the thermodynamic properties along with velocity, mass flow rate. The second line shows the compressor properties, calculated properties along with the with what we provided. You can see the work in, meaning power requirement is 2.45 megawatts. The second law efficiency is 88.2, and reversible work is 2.16 megawatts. In this last example, we're going to see how to utilize ThermoFlo to perform thermodynamic cycle analysis. Here we have a two-stage refrigerator that operates between the pressure limits of 0.14 and 0.8 megapascals. The working fluid is refrigerant 134A. The refrigerant leaves the condenser as a saturated liquid, is then throttled to a flash chamber that's operating at an intermediate pressure of 0.32 megapascals. The vapor is extracted from the chamber is mixed with the refrigerant leaving the low pressure compressor, and then the combined flow is compressed in the high pressure compressor to the condenser pressure. The liquid leaving the flash chamber is throttled to the evaporator pressure. Assuming the refrigerant leaving the evaporator is a saturated vapor and no losses in the compressors and connecting pipes, we want to determine per unit mass of the refrigerant, the mass fraction of the vapor leaving the flash chamber, the amount of heat removed from the refrigerated space, the compressor work, and the coefficient of performance of the cycle. First we start ThermoFlo and then click on Create Model, give it a name like Ref 2 Stage for a 2-stage refrigerator. Click on Save and we choose Thermodynamics. Now we pick a compressor, place it on the canvas. Then we need a condenser and a valve. We place the valve next to the condenser to bring the pressure down to the flash chamber pressure. And you can line things up to make them look better. Then we'll take another valve to bring the pressure down to the low pressure compressor. And now we need an evaporator. Then a compressor for a low pressure compressor. And now we need a mixer. We pick a mixer from the component list and place it on the canvas. Okay, let's just move things around a little bit to line them up better. Now all we have to do is to get the outlet of one and connect it to the inlet of the next component to complete the cycle. And here, connect the compressor. Compressor goes to the mixer and the mixes with the flash chamber. Okay, now we can move things a little bit around to line them up better. So this completes the cycle. So now we need to choose a fluid. Right click, set fluid. Double click on that. Default fluid is water. We need a refrigerant. So we go to the list of refrigerants and scroll down and let's pick R134A. Click on select fluid and here we have fluid set. Now we need to do analysis per kilogram, so we go choose mass flow rate and set that to 1 kilogram per second and put these out of the way. Now let's set the pressure levels. The lowest pressure go into the compressor, set that at, so we choose the pressure, double click on it, set it at 0.14 megapascal, apply. And now we set the high pressure. Right click and double click on the pressure icon. We set that 0.8 megapascal and we'll apply that there. Now we can move the pressure out of the way so we can see the labels more clearly. And the intermediate pressure is at the flash chamber. It can be set any of the places. So we choose it at the inlet, set that 0.32 megapascal and set and press apply. Okay, so we have now set all the pressures in the system. Now assuming this is the ideal system, we know that refrigerant coming out of the condenser is saturated liquid, so we set the quality to 0. That's the default value, so we don't have to do anything there. And leaving the evaporator go into the condenser, we have saturated vapor. So we similarly pick quality, double click, and we set the value to 1. That completes the circuit. We're ready to analyze. Now just let's double click on some of the components. You can see that for ideal compressor we have no heat loss, 100% efficiency, and we don't need to change anything. Similarly, you look at the condenser, we don't need to set any of these values. If you wanted to calculate the losses, you could, but we're doing an ideal cycle. Press on run, and it's done. We can press yes to view the results, and that shows the temperature. You can change the results display to anything you like. You choose enthalpy, temperature, whatever. If you right click on any component, you can get the detailed result of that component. So here's the high pressure compressor. We have the work, which is equal to the isentropic work, and there we go. To see the detailed results, we can open the out file and view the results from there. Here the results are extracted and shown here. EPs stand for endpoints or junctions between various components. So you can see the pressure, temperature, specific volume, internal energy, enthalpy, entropy, quality, and mass flow rate and volumetric flow rate here displayed at all of these locations. To view the component results, you can move down in the out file to the components section. Now here we are looking at the detailed results of the components. We have two compressors, a condenser, an evaporator, a mixing chamber, a flash chamber, and two valves. If you look at the results of the compressor, we can see the power in is displayed, which is the same as the isentropic power because we chose to have an efficiency of 100%. Kinetic energy and potential energy changes are not calculated because we chose to neglect them. Same in the condenser, you can see the heat loss in the condenser is calculated. The minor losses and all the other losses are not available because, again, we chose to not include those in the analysis. In the evaporator section, you can see the heat into the evaporator is calculated, which is the same as the amount of heat removed from the refrigerated space, and similarly the other components. At the bottom, you can see that the COP, or coefficients of performance, is automatically calculated by the software. It recognizes this is a refrigeration system, so it calculates COP. And you can see for a refrigerator, which we are interested in, is 4.4753. If this same problem was solved as a heat pump, the COP would be 5.4753. So this completes this exercise. Thanks for your attention. If you have any questions or comments regarding this webinar, or if you would like additional information about ThermoFlo, please feel free to contact us.